You know, when I was younger, I wondered, well, what is the world made out of? And as it turns out, the world is made out of atoms. Then I wondered, well, are atoms made out of anything? And it turns out that they're made out of protons, neutrons, and electrons. Well, and then I wondered, is this really it? Is this what the whole universe is made out of? Well, not necessarily, as there are actually these things called fundamental particles, which everything that we know of is made out of, including protons and neutrons. You see, protons and neutrons aren't fundamental particles at all. In fact, they're made by two different types of particles called quarks. There are 6 quarks: up, down, charm, strange, top, and bottom. Protons are made out of 2 up quarks and 1 down quark, while neutrons are made out of 2 down quarks and 1 up quarks. Most quarks, other than up or down, are too unstable to form particles like protons and neutrons, so you won't find them out in nature naturally. Muon and tau particles are essentially heavier versions of the electron. They have more mass than the electron. While neutrinos are essentially doppelgangers of these 3 particles. They have very little mass and they don't have an electrical charge, meaning that they don't interact with the electromagnetic force. Altogether, there are 6 leptons. The strong nuclear force is responsible for holding quarks together to form protons and neutrons. It's also responsible for holding protons and neutrons together in the nucleus. Electromagnetism is what keeps electrons orbiting the nucleus, and it's also responsible for giving particles their electric charge. The weak force is a little bit more complicated. It's essentially responsible for certain types of radiations and how particles decay into more stable particles. Gravity, as we know, is what causes things to fall, and it's what causes planets to orbit stars. Some actions caused by the forces are carried out by particles, but not ordinary particles. No. You see, quarks and leptons are collectively called fermions, but there's a different type of particle. See, have you been wondering where the photon has been all this time? Well, there it is. See, the photon belongs to a group of particles called bosons. Along with the photon, there are the gluons, the W and Z bosons, and the Higgs bosons. The photon is the force carrier for electromagnetism. Funny enough, the photon doesn't have an electromagnetic charge. The photon has no mass, meaning that it travels at the speed of light, because it is light. The gluon is the force carrier for the strong force. The gluon has what is known as color charge, basically the strong force's version of electromagnetic charge. The gluon is what holds quarks together, and it also has no mass, which means it also travels at the speed of light. Huh, look at that tree. Oh no. Wish me luck. Nice. W and Z bosons are both force carriers to the weak force. They both have mass. The Z boson does not have an electric charge. However, the W boson can have an either positive or negative 1 electric charge. Gravity doesn't have a force carrier like other forces. Now, speaking of gravity, how am I going to get down from here? Whoa. Well, I forgot to mention the Higgs boson. The Higgs boson isn't a force carrier. It turns out that the Higgs boson is part of what is known as the Higgs mechanism, which is how particles get their mass and stuff. But I don't want to go into too much detail about that. Well, what I've just described to you, all these particles interacting with each other with forces and stuff, is known as the standard model of particle physics. It basically describes how these 17 particles interact with each other throughout the universe. You know what's funny? These particles are theorized to only make up 5% of what the universe is made out of. Well, dark matter making up 25% and dark energy making up all the rest. Well, just goes to show, throughout all the years of discovery, the human race has only observed 5% of the universe.